In this video, we're going to go through the motions of taking a data set, entering it into our calculator, deciding what type of model best works with it, and then producing that model using technology. So let's start with this example. It says the following data gives the heights and weights of 17 male students. And wants us to find a linear model or regression line for this data. Okay, so we kind of jumped the gun here by saying line, but we'll get this look at this data first off and then kind of agree with what they've already stated here, that it really ought to be a line that fits to this data. But before we do that, we need to make sure we understand which of the variables should be our independent and dependent variables. So remember, the independent variable is always going to be the x, right? And the dependent is always going to be the y. Okay, so when we think about this, you should think about, okay, does it make sense to say that height depends on weight, or does it make sense to say weight might depend on height? And clearly, saying weight might depend on height makes more sense, right? Because if you get an inch taller, you necessarily have an inch more of some amount of body mass, right? So your weight kind of has to increase in that sense. So we would say that y is going to be our weight. And then the independent variable we'll regard as the height. All right, so when we've got our set of data, we're going to put this in our calculator, remember, by hitting the Stat button and then selecting Edit. And then if you've got anything old in your calculator, just go ahead and highlight the name of the list and hit Clear and then Enter. And then again, highlight the name of the list, hit Clear and Enter. Try to avoid hitting Delete. That'll actually remove the entire column, and you'd probably rather not do that. So it's good practice usually to put the X's in list 1 and the Y's in list 2 just to kind of keep it all straight. So I'm going to put my heights in list 1. And magically now it's all complete, just because you don't need to see me entering all of them in individually. All right, so what do we do now? Okay, so as we said, we're always going to store the independent variable, or the x, in L1 and the dependent, or y, in L2. We went ahead and entered it using the stat edit, as we said, so this is just bolded list to remind you of everything. All right, but now we're going to take a look at the data. So we're going to make sure that plot 1 is turned on, and we're going to hit second stat plot in order to take a look. So stat plot is the second function of the y equals button. So I'm going to hit second stat plot. And right now all my plots are off. So I'm going to press enter on plot 1. And there's got a toggle here for off and on. So select on and press enter. Make sure the type of graph that you have is the scatter plot type, which is the first one there. And then just make sure that your X list is list 1 and your Y list is list 2. So if it wasn't, like, just for example, like let's say it was blank or you had something else in there, then the way you do that is do the second function of the number 1 to get list 1. So I'd go second list 1, and you can see down here all these different lists are just the second functions of their respective number. So make sure it looks like that. And then in this bullet here it says zoom stat will automatically adjust the y values to show the data. So if you go to the zoom button and go down to zoom stat, number 9, then it'll automatically zoom in on the right spot of the graph for you. All right, so so this data here, it's kind of scattered there. It seems like a line would be reasonable to put to that data. I don't see any kind of curving happening. So when they told us to make a linear model for it, I think that was wise. All right. So how do we do that? If we want to fit a line to the data, what we're going to do is we're going to say stat and then calc and then lin reg. Okay. So we go to stat just like when we were entering the data in, but then we're going to toggle over to calc, and then we're going to click on lin reg ax plus b. All right, and again, we're going to make sure the X list and the Y list are our list 1 and our list 2, as they're supposed to be. your frequency list should be blank. Mine right now is not, so I am going to hit clear to make sure that that goes away. And then what we're going to do is we're going to store our equation. Okay. Now I realize not everybody has the calculator screen in front of you that I do. So some of you, when you select linreg, it just takes you back to your home screen and it just says linreg ax plus b. Okay. So if that's you, what you're going to do is before pressing enter, you are going to do the same set of commands I'm about to show in store equation. Okay, so what I'm going to do on my calculator screen is I am going to type y1 into that spot. So for those of you who don't have that screen, you're just going to type y1 right after linreg ax plus b. And to do that, you follow that sequence of commands there. And then after you get y1 in here, that's when you're going to go ahead and press enter. All right, so what I do to get there is I click on this vars button. So vars, and then you toggle over to yvars, and then you select the function button, and then you can select y1. And then once you're done with that, if you have a screen like mine, you hit calculate, and if you have a screen like this down here, then you just hit enter. But either way, we should both be seeing the same thing here. We should be seeing y equals 8.72x minus 438. I guess we'll just say 0.0. Okay, so there's our equation, right? So if I put a height in for x, this is a height, right? Then it's going to tell me the weight that goes along with it. And now if I go back to the graph, I hit graph again, it has the line going through it. And so by typing y1 in after linreg ax plus b, basically that stores the equation we come up with in y1 so that it'll show up on the graph for us. Okay, so there's our line passing through our data set. Okay, now on the next page here, it asks us, what is the correlation coefficient for the data, and what does this tell us about the association between the two variables? Okay, so we'll talk about how to find it in the calculator in just a moment, but just some basic principles first of all. The correlation coefficient is the number r, and it ranges from -1 all the way to 1, and then there's everything in between. So -1, we'll say like -0.8, right? -0.30, right? 0.7 all the way up to 1. Okay, so it goes all the way from -1 up to 1. Okay, so what happens is an R value of 0 means there is no apparent relationship or no apparent association between the values at all. So this picture right here is what it would look like if the correlation coefficient was 0. Okay, this one right here, this one might be like R is 0.75. It's positive because there's definitely a positive slope, but it's not a super strong correlation, right? The data isn't too tightly compact together. Whereas this one right here might be something closer to like R equals 0.9, right? So it's positive because there's a positive slope, but the data is a lot more tight. In other words, I'd feel more comfortable making predictions about my Y based on my X. All right, and then this one here, it's definitely got a negative slope, right? So, I don't know, we'll call this R equals -0.65, just to throw a different number out there. And then this might be like R is -0.8, 0.88. Okay, so getting closer to -1. So the closer you are to 1 or -1, the stronger the relationship is. Negative meaning it's a negative relationship, and positive meaning it's a positive relationship. Okay. So it's nice to know what is the correlation coefficient, right? How strong is the relationship that we're seeing? Okay. And so in order to find it, what you do is you make sure that you have your diagnostics turned on your calculator. So what I do is I hit second catalog, and catalog is the second function of 0. And you've got this big long list here, and I'm going to scroll down until I get to the D's. And I'm going to select diagnostic on, and I'm going to press enter. Now what that just did is seemingly nothing, but what it does is now every time that you produce your equation, it's also going to tell you what the R value is. So if I go back and do the same steps to get my equation, so I go to Calc, Linear Regression, L1, L2, and I store my equation in Y1, and I hit calculate. Now it just doesn't just give me the equation, it also gives me this thing called R squared and then the R. The R squared is important in data analysis, but we're not going to worry about it. The R value is the one we're talking about here. So what we can say is for our little problem that we're doing, R is 0.646, we'll say. And if I click on the graph again and kind of look at how this is spaced out, you know, kind of similar to how this is spaced out, so you can kind of see the relationship here between the number I kind of made up and what we're seeing in our data set. So what we would say about this is that there is a positive, because there's a definite positive slope, but I would say it's not a super strong relationship in that the data isn't too tightly held together. So there's a positive, we'll call it moderate relationship between height and weight. And I think that that kind of goes with our experiences, right? You know, of course, you know, people who are taller are going to weigh a little bit more, right? Height has a lot to do with it, but there's a lot of other factors that affect our weight as well, like, you know, what kind of exercise we do and that sort of thing. So so it kind of makes sense that, yeah, height is a pretty decent predictor of weight, but it's not perfect. All right, so now what we're going to do is we're going to talk about the equation we came up with and apply it to some problems here. So let's go back for a moment and just remind ourselves, we can do this in the calculator, right, of what our equation was, right? It was y is equal to 8.72x minus 438. So first of all, what is the meaning of the slope? Well, this is something that we've done in this class, right? We know that the slope is the number we're multiplying x by, and I think it helps, remember, to say that 8.72, we can force it to be a fraction. And the reason it's helpful to force it to be a fraction is because we can then remember that, okay, the 8.72 is the change in y, right? And the 1 is the change in x. Right? But of course, what is y and what is x? Y is the weight and x is the height. So what I can literally say is that for each additional inch in height, right? That's the change in x part. We expect about an 8.72 pound increase in weight. All right. And then part D says, what does the model predict the weight of a 70-inch tall male student is? Now, we've done this manually many times, so I want to show you kind of a slick way you can do this in your calculator. Is we have this equation, right, that we know that if we plug a particular height into it, then it'll spit out the y value, the weight. So what you can do is say that your weight here, or your y value, is going to be taking the equation y1 and putting 70 into it. So in your calculator, you can just go back to your home screen and then pull up y1, go ahead and do the vars, yvars function y1. So you can get that on your home screen. And then in parentheses, just put 70. And that'll be telling you to or telling your calculator, go get the equation, put 70 in for x, and tell me what the y value is. And what we get here is a y value of about 172.6 pounds, right? And then part E says if a male student weighs 155 pounds, how tall would we expect him to be? Okay, so now they're telling me that y is 155, right? So what is x? So to do this, what we can do is use our graph. So if you go to your y equals menu, and in y2, go ahead and put 155 as the y value. And then if I go to the graph, you'll see the original equation and 155. So if you just ask the calculator, where do these two lines intersect, then that'll tell you what the x value should be. So you just go to second calc, intersect, and then it just asks for the first curves. Okay, so hit enter for the first curve, then it goes down to the red one. Is this your second curve? Yes, so I hit enter, and then I'm just going to get near the intersection point and press enter, and there we go. X is about 68, right? X is about 68 inches. Now, in both of these cases, if you want to just do this manually, right, in this case, you would have just said y equals 8.72 times 70 minus 438, and then would have gotten basically pretty close to that answer. Or if you would have gone 155 as the y is equal to 8.72x minus 438, and solve for x, of course, that'll get you the same answer. So I don't care if you do it that way, but I just wanted to take this chance to kind of show you how you could use your calculator to get that same information. All right, so one more example here. It says the following table give the number of hours since the peak concentration of aspirin in the bloodstream, and the concentration is in milligrams per 100 cc's of blood at each time. So let us find a model that fits this data. Okay. So first of all, I'm going to clear off everything that we've done here in the previous example. So let's clear out our old y values. And then I'm going to go to our table and just highlight list 2, hit enter, clear, hit clear, enter here. So it's all cleared out. Now let's go ahead and put in, I think it's clear that time should be our independent variable and concentration should be our dependent variable, right? So let's go ahead and put in all these times in for list 1. And then put these concentrations in for list 2 as the y values. And then you can see in the question they're kind of telling us that we should look at this data as exponential data, but let's first take a look at the scatter plot ourselves to see if we kind of agree with that. We'll make sure, again, our stat plot is on, right? List 1 and list 2 are what we're looking at. So remember, to zoom in on this data, we hit zoom stat. All right, so I'm looking at this, and at first maybe even tempted to put a line to it, but I think if you look at it a little more, you can kind of see this exponential decay type curve that might fit well with this data. So I think it's reasonable to go ahead and try to fit something like this, a b to the t. So if you go to stat again, go over to calc, then you can fit an equation that looks like that by going to exponential regression. So that's number 10 in mine. So exponential regression, and again, some of you may have this screen, some of you may not, but we just do the same thing as the last one. I want to store my equation in y1, so I go vars, yvars, function y1, and then I hit calculate. So what it's telling me is that we have y equals 15.27. That's my A, right, the initial amount, times B, which is 0.828 to the t, right? So as it says, interpret the vertical intercept, right? So the vertical intercept, and actually let's go ahead and put this in the form that it's kind of asking for. They said t and then concentration c. So let's express this as a function of time. So the vertical intercept is, of course, when we plug 0 in for t, right? So 15.27, 0.828 to the 0 would be 15.27, right? And that's milligrams per 100 cc's of blood. And so what we're saying is that this is the initial amount of aspirin in the bloodstream. Okay. I don't know what's going on with those lines, but you can still read it. So the initial amount of aspirin in the bloodstream. Then it asks, when will the concentration fall below 2.5 milligrams per 100 cc? So they're asking us when, right? So that's a time. Will it fall below a C value of 2.5, right? So this is like that problem we did before where we can go to our calculator and in Y2, go ahead and put the concentration value that we are interested in. So if I go to my graph, okay, you can see what's happening here is my graph has zoomed in on the data. It's put my exponential function fit to that data, and then it's graphing way down at the bottom here this 2.5. So what that's telling me is that the screen that I'm looking at right now is insufficient. First of all, it's going to cross the exponential graph further out here, so I've got to expand my x's. But I also need to expand my y values or my concentration values as well to be able to see the intersection. So I'm going to go to the window and notice that I'm only going to 7.7 hours, so let's up that. Maybe just, how about we go to 24 hours? That makes sense, right? And then for my y minimum is at 2.481, so almost already at the 2.5. So I think we want to reduce that down to 0. And if I do that, now I can really see what's going on here, right? And so I can go second calc and find the intersection here. First curve, second curve, and then get close to my guess. And it says the intersection's happening at an x value of about 9.6 hours. Okay, so what we can say is t is about 9.6 hours. All right, the last little note I'd like to make here is it says, if we suspect that data points are exponential, then a way to check to see if we're really correct about that is to plot the points x natural log y. And if we do, those should be linear. Okay, so first let's do this to the data set that we've got in the calculator, then I'll explain why it's true. So I'm going to first of all clear out everything here because we got a lot of stuff going on. I'm going to clear the equations out. And I'm also going to turn this plot number 1, I'm going to turn it off for a second. Because instead of looking at the original data points x and y, I want to look at x natural log of y. So the quick way to do that is to go to Stat and Edit. And then in list 3, what I'm going to do is I'm going to highlight the title and I'm going to type in the natural log of all of the y values. So that would be the natural log of list 2. Okay, so I'm taking all these y's, right, and taking the natural log of them. And if I do that with the title highlighted, it'll automatically fill them in for all the values. So if I want to plot these, then x we know is still in list 1, but the natural logs of y are in list 3. So what I can do is I can go to my stat plots again, so second stat plot, and this time I'm going to use plot number 2, just not to get it mixed up with plot 1. So I'll turn it on, and then this time what I'm going to do is I'm going to do list 1 as my x list, but then change my list 2 to list 3. And that will plot x with the natural log of y. So if I do that, and I hit zoom stat, like I have before, if you look at that, that data looks pretty linear. So what that means is that, since we'll say it this way, since x natural log of y looks linear, looks like a line could go through it, we are confident that x and y are exponential. Okay, so why would that be? The reason is if you have exponential data, y equals ab to the x, oops, and you take the natural log of both sides, then you get the natural log of y is equal to, first of all, using the addition rule, the natural log of a plus the natural log of b to the x. But then you can also bring the x down in front. So the natural log of y is equal to the natural log of a plus x times the natural log of b. And if you can just remember that the natural log of b is only a number and the natural log of a is only a number, then what you have is the natural log of y equals a number plus x times a number, which is linear. Right? That's a linear equation. So because of that, whenever you plot x's and natural log of y's, if they do in fact appear to fit in a pretty good line like this, then that gives you more confidence that your data set was exponential to begin with. So kind of an interesting fact there to go along with this and kind of confirm what you think you're seeing in the scatter plot itself.